for the differential op-amp, there are 4 types of input resistances. Let's start with this one. Calculate the input resistance on this terminal. Now I'm going to follow standard procedure and set all independent sources to 0, alright, ground this, and apply a voltage of Vx over here, measure Ix in relation to Vx, and find by this the equivalent input resistance. This is akin to the Thevenin resistance from circuit theory, if you remember. Now, because we have an op-amp here, we have 2 inputs, alright? This is the non-inverting input and this is the inverting input. And because we assume the gain is high, alright? The gain is high, the op-amp is ideal, therefore these voltages must be the same. Now, I said that this voltage is 0. Why? Well, because if this point had any other voltage, so let's say this point had 5 volts, it would mean that this point has a higher voltage than this point and this point at the same time, which means there should be a current flowing from here all the way to here and a current flowing from here all the way to here, alright? Because this point has a higher voltage than here. But we cannot have at the same time a current flowing like this and like this, because there is no source for this current. So from the non-inverting input, there cannot be a current flowing like this and then splitting into something else. Alright? Because it's an ideal op-amp. Since no current can flow from the op-amp, and the current has to either flow in these 2 directions, or if this voltage is more negative than the ground, so if it was minus 5 volts, the current had to flow like this and like this. So it would have to flow from both directions into the same node. Alright? Which means this point can never have a voltage other than 0 volts. Alright? This would violate the KCL as we know it. Anyway, performing Ohm's law for this resistance over here, we have that Vx minus V minus over Ix must be equal to R, alright? Now how much is V minus? V minus is 0, alright? We said previously why. Therefore now it's very easy to calculate Vx over Ix because that's R in. Vx over Rx is R, alright? We find this very, very easily. On to the second case where we need to find the input resistance over here. We follow the same procedure, set V1 to 0, alright? Put a voltage source over here, calculate the Ix in relation to Vx and calculate the R. Now, this case, well, we have a voltage here and a voltage here, and we can go ahead and try to find the equivalent voltages here like we did before, alright? But turns out that the case here is much, much easier. Why? Because this voltage is applied in the 2 ends of 2 resistors which are connected in series, alright? Why they are in series? Because this current that starts from here and enters into here has to flow downwards. It cannot flow inside the op-amp. So since these 2 resistors are connected in series, have a common current, and both of these ends are connected to the battery, alright, since the ground means that this terminal is common here, alright, I can simply say that these 2 resistors are in series and takes Ohm's law for these resistors, which would be Vx over Ix is equal to 2R. This is only true because the current is common, alright? And no current flows from or outwards from the non-inverting input of the op-amp. That's it. Very, very simple. Just so we remember this. Now for this case, what I did is basically change the input voltage into a Vx, alright? Just change the name of the current source, of the voltage source. Didn't do anything different, alright? And we measure Ix relation to Vx, just so we find Vx over Ix. This is very strange, alright, at first sight, because we have a negative terminal connected to the circuit and not to the ground. But don't worry, we'll figure it out. First step is to name these points as point B and point A. Alright? Why? Well, now I can define Vx as a Va minus Vb. And now I can make my life much, much easier. Now, it's very important to not forget here, it's not Vb minus Va, it's Va minus Vb. Alright? This voltage has the same value as this voltage, alright? The ideal op-amp with infinite gain. And now, this current, let's notice it's the same current as the one starting from here, from the ground, goes all the way to here, cannot flow inside the op-amp, so it goes all the way to here, then it goes, and flows all the way to here. And then it goes somewhere, does something else. It doesn't flow inside the input. Alright? So this makes my life much, much easier, knowing that this current is the same everywhere. I can take Ohm's law now for all resistances. So Ix must be 0 minus Vx, minus V plus, over R, which must be equal, because the current is the same, to V plus minus Vb over R, alright, this resistance, which must be equal to Va minus V minus over R. Again, because this current is the same. Notice that in these cases, alright, in these circuits, we work with a current. We look at where the current goes and where it flows. It is key into our understanding to how to find these input resistances. Alright, now I can say this and this are equal, alright, these are typical equality. Therefore, I can solve in relation to Vb and say that Vb is equal to 2 times V plus, alright? Key here is to eliminate Vb and Va from my future equations, alright? Now, I take this and say that these two are equal, alright? These two are equal. Therefore, 0 minus V plus is equal to Va minus V plus. V plus is equal to V minus, therefore this simplifies with this, and Va is equal to 0. Now, I'm ready to calculate Vx over Ix. Alright, this is the input resistance. How much is Vx? Va minus Vb. How much is Va? 0 Vb, 2 V plus over Ix. Turns out to be minus 2V plus over Ix over here. And how much is V plus? Well, V plus from this equation, from where? From this, alright, is equal to minus R times Ix. You see it from here? And I replace it over here. Now I can eliminate Ix and Ix, alright? I eliminate this, and I have that Rin is equal to plus 2R. Note, then this is important. In case we had a negative input resistance in an op-amp circuit in general, alright, this would not mean that this is a confirmation of whether we did something right or wrong. So if I find a negative input resistance or a negative output resistance, it would not necessarily mean that I have made a mistake somewhere. This is very possible in op-amps, in op-amp configurations. It can happen that we notice some negative resistance at the input or the output of the circuit. It can happen. This doesn't mean that this is a physically negative resistance. Let's not forget that inside these op-amps there is a current source, alright, there's voltage sources, things like that. No law is being violated, alright? But if we found something negative here, the point is but it would not mean that we made necessarily a mistake, all right? Okay, now you are not going to remember this just by seeing it once. I suggest, no, I demand that you go ahead and try to solve this by yourself right now. Pause the video, return back, and try to do the same thing by yourself. And then come back again and try to see if you did the same, if you found the same result over here. Where have you made the mistake? Where were you stuck? All right. This requires practice. For your exams, you will have a very hard time remembering this if you see it only once. All right. In your exams, you will probably have a resistance value here and here and here and here, all right, of 100 ohms, 200 ohms, etc. So you cannot just say that Rin is equal to 2R, right? This will not hold true, all right, in any other case. This holds true only where these resistances are all the same, of the same value. All right, moving on to this final case over here. I'll do the same thing as I did before, and I set and change this voltage into a Vx. I'll name this Vx. I measure Ix relation to Vx, just so I find my input resistance over here. Now, first thing I do, I name this point as node X, and then say that this current Ix splits into two currents, I1 and I2. Uh-oh, it's not the same as previously, right? Where I had the same current. Will this make my life difficult? Well, we will see. We'll see. This point has the same voltage as this point, all right? I know from the case, it's simple KCL at point X, that Ix is equal to I1 plus I2. How much is I1? From Ohm's law, very simply, Vx minus V minus over R. All right? How much is I2? I2 is Vx minus V plus over R. And since this current is the same current that flows from here all the way to the ground, it will be that I2 is equal to also V plus minus 0 over R. Right? You see it why, hopefully. Now, from this equality, I can find out that Vx is equal to 2 times V plus. Right? This simplifies. Vx is 2 times V plus. Now I'm ready to find the input resistance. Why? We'll see now. Vx over Ix must be equal to Vx, alright, the input resistance, over the input voltage, over Ix, which is equal to I1 plus I2. How much is Vx? I found this earlier in relation to V plus, so it's 2 times V plus. How much is I1? I found it previously, Vx minus V minus over R. How much is V minus? V plus. How much is Vx? 2V plus. Over R plus, alright, plus I2. How much is I2? I found it earlier. I'll use this equation here. V plus over R. Alright. Note that I put all of my unknowns here in relation to a common value, a common unknown, V plus. This V plus can be simplified from everywhere, and Rin is nothing but R, the resistance R. And that's it, very simply. I found it. Again, the only way to remember this is by practicing. Practice, 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 practice. Wind back the video, try to solve it again, because again, in your exams, you will have some actual values over here, so it will be very difficult to do this again if you don't remember how we did it. All right? That's basically it. That's a way to find the input resistance in the differential amplifier, all right, in 4 different cases. Now, you can apply these methodologies in other similar op-amp topologies, Alright, to find the input resistance. For the output, things are a bit different. I'll prepare a video for this. Don't worry about it. Alright, check out the op-amp playlist over here for more op-amp videos. Study well and take care.